All right, so we are doing a free body diagrams worksheet. So when we are going to be, the main portion of this, we're going to be drawing in free body diagrams. A couple little notes. If an object is speeding up to the right, the acceleration needs to be the right, which means the net force also is to the right, aka the right force needs to be larger than the left force. And the up and down would need to balance. If the object is at rest or constant velocity, that is something you guys do need to know. All right, if this object is at rest or constant velocity, the net force needs to be 0. Okay, all forces must balance. If the object is moving to the right but slowing down, the net force would have to be to the left, so the left force would have to be larger to the right if there is even a right force there. Now, in this scenario here, on this case, first thing they ask us to do is in each one of these situations determine what the net force is. So opposite forces we subtract, same direction we add. You have 3 newtons going up, 3 newtons going down. Those two forces balance. So to show forces balance in opposite directions, you guys are going to add in these little equal signs. So you would add these into that drawing. If you have 5 left and 5 to the right, they're balanced, they equal. So what would the net force on this be, y'all?
0.
Yes, very good. And we would write in over here 0 newtons. Situation B, top and bottom are both the same value, same magnitude, so they balance. And so what would the net force be? 5, good. In what direction? 5 newtons to the
Right.
what? Left, yes. C, we got 20 up and 20 down, balanced. So what would the net force be? Very good, 0. And C, you have 40 up and 25 down, opposite directions we subtract. 40 minus 25, 15. But what direction would the net force be? Up, because the upward force is larger. Okay, we had done this one as our do now, so if we run through this super quickly. They want the net force to be 0. Which means everything has to balance. So that means A would have to be 50 newtons, right, going to the left. That means B would have to be 200 newtons to the right. Here, they want the net force to be 900 newtons. So that would mean that C would have to be 1100, because 1100 minus 200 would give us 900. And since this is the higher magnitude, the direction of the net force would be up, so C 1100. They want the net force to be 60 to the left, which means the left side force needs to be 60 greater than the right side. So 80 minus 60 would give us 20. And you could always go back and double check. 80 minus 20 is 60, and 80 is bigger, so it would be to the left. That would be correct. Now, for E, because the net force is when the net force, guys, is left or right, that means the top and bottom, they have to balance. So if we have 300 up, E would have to be 300 down. And then this last one, net force is 30 newtons to the right. That means the right side force needs to be 30 greater than the left side. So 30 and 20 together would give us 50 newtons. So G would be 50 newtons. And F and H, because there are arrows, that means there is a force, so we can't put 0. If there was 0, there would be no arrows, like over here. There's no force left or right on this one. But because there are arrows, we do have to put down a number. It can be any number as long as F and H are the same. So I'm just going to put down 25.
What was the first one?
Now we get into this main piece, the drawing. So I have handed you guys this note piece, this little thing of notes on some of these forces that we're going to look at and have to be drawing in. So the normal force, F subscript capital N. The normal force is a support force that's exerted on an object while it's in contact with another stable object. It's usually from the surface. Now, it's always perpendicular, which you should have just looked at in the one quiz you took, which makes 90 degrees to wherever. So if it's completely flat, 90 degrees is straight up. We have our little 90 degrees. That's why the normal force is straight up right there. If the wall is like this, that's why it's straight out. And then if it's on a incline, like this surface, right, it's upwards in that direction, making it 90 degrees. But we are probably going to mostly see everything on either a flat surface or moving through the air. So in this worksheet, anytime they say something's on the ground, on a table, on a desk, a road, gravity, we always are going to draw straight down, right? We make our square. We always draw gravity straight down. And if it's on a flat surface, ground, table, whatever, normal force is going to go upwards. It is going to be the same length, and they're going to be equal. All right, on a flat surface, those two are equal. Every single one of our free body diagrams will have the object is going to have a mass, so it's going to have a weight, and we always draw Fg going straight down. And then we'll get into the other parts of our forces, but the main ones, other ones that you will see on today's worksheet, okay, are applied force, which is a push or pull force, friction, which always goes opposite the direction of motion, and then air resistance. Okay, so let's look at it. A book is at rest. On the front of this worksheet, we just talked about at rest is a key phrase. That means that the F net has to equal 0 newtons, which means everything must balance. Okay, so I'm going to just draw a flat piece of surface. So it could be a book, it could be a desk, it could be a road, it could be the ground. All right, whatever. Now, whatever our object is, the object is a book. So instead of always just drawing whatever the object is, we just draw a square with a little dot in the center. And from that center point, we make all this stuff come out of it. All right, so first thing you should always do is on your box, your square, your free body diagram, always we're drawing weight downward. Weight is Fg. Now it's at rest, so that means the net force is going to be 0. If I just left it like this, is this balanced? No, right? To balance, you need to have two things that are equal and opposite. Well, if we just left it like that, this answer would be incorrect. So the net force has to be 0. So that means we have to have a force going upwards. All right, approximately the same length. Now, what would that one be? It's on a flat surface, so we would use the normal force, Fn. So it would be Fn that goes up, and we want to show that they're equal, so how do we do that? We're going to put a little equal sign through both. And that would be your first one, okay? And that is it. The next one, an egg is free falling from a nest in a tree. Neglect air resistance. So we're basically saying, okay, air resistance doesn't exist right now. It's like falling in a vacuum. Draw a free body diagram for this. All right, so we're not on a flat surface anymore. We're flying through the air. So here's our egg. What is the one thing you should always draw in? Down arrow for the weight, and what do we label that as? Fg. Now, air resistance is a type of friction in the air which would go opposite the direction of motion, but guess what? They said neglect it. Pretend like it's not there. So guess what? This one, done. All right, when they say neglect something, we're not including it as a possibility. All right. Now, this would be kind of going back to what our free fall problems look like if we were to throw something upwards in the air, straight up. All right. Does this right here mean that the object is moving downward? Does this diagram mean that the object is always moving downward? No, it means that the net force is downward, and that's where the acceleration is. So, guys, remember, think about it. If you throw something straight up, does gravity pull it down? Right, gravity's always acting down. That's why when you throw something up, it slows down, gets to the top, hits 0, and then starts to speed up on the way back down. So, like this object, if we were, not this example, but we had a free body diagram for something we threw straight up in the air, it would be like this if we neglect air resistance. We throw it straight up, because as soon as it leaves our hands, there is no applied force, it's just the force of gravity. So this thing would go up, slow down, get to the top, and start to accelerate again back downward. The acceleration is downward. not always the motion. Most of the time they're in the same portion though. This one, a flying squirrel, basically is just going to fall, swoop to the ground. And key phrasing here is constant velocity. Constant velocity, just like at rest, means the net force is going to equal 0. So again, everything must balance. Yeah, that's right. This time they're telling us to consider air resistance. All right, so here is our flying squirrel. First thing we should do, guys, is draw what? Downward arrow. And what do we label it? FG for the weight. All right. You'd be like, okay, I got that. I know I'm supposed to always draw FG. Super easy. Now, constant velocity. You need to remember that. All right? That means the net force is 0. So, what do I have to draw in? If everything has to balance, do I have to draw an arrow to the left, to the right, or do I need to draw one up? Up. And do we want it to be the same length? Yes. Now we just need to figure out which one we're drawing. Okay? If you're on a surface, you would draw it and label it as the normal force. But if you're moving through the air and it tells us to consider air resistance, then we are going to use F subscript air. All right? It's a special type of frictional force that acts as they travel through the air. All right? And it is often observed to oppose the motion of an object. Okay, so instead of Fn, we are going to write F subscript air. I would say that's pretty fair. Yeah, no, that's bad, I know. All right, and how do I show that they're equal? How do I show that they're balanced? Yeah, equal sign. And you are good on this one. The next one. Okay, we got a few things going on in this problem. We have a rightward force. All right, we have a rightward force applied to a book in order to move it across a desk. So we are on a flat surface, and it's going with a rightward acceleration. So acceleration, anytime we have the acceleration, the net force is always going to be in the direction of the acceleration. So when we do have an acceleration and they tell us that, all right, acceleration is in the direction of the net force. So there is going to be a net force on this, which means the arrows are not all going to be the same length now. So, are we on a flat surface? Yeah, because we're moving across a desk. So I'm going to draw my flat surface. I'm going to draw in my object. In this case, that's our book. Draw my little dot in the center. First thing you should always do, tell me, down arrow, FG. On a flat surface, it's not moving down or up, right, off that surface. So it needs to get balanced out. What does it get balanced out by? Fn, which stands for the normal force. I'm going to show that those two are equal. Okay, now telling us a rightward of force is applied. So I know there's going to be a right arrow, but what kind of force and how big do I need to make it? So it also says in here to consider friction forces. All right, just to borrow. So this is like the one that's slightly tricky. But once you see it a couple times, it's not bad. A rightward applied force, right? That's a push or pull. So they're saying that's going to the right. It's causing a rightward acceleration. On the very front of this, we had written that if an object is speeding up to the right, the acceleration needs to be to the right here, which means the net force is to the right. That means the right force needs to be larger than the left, and the up and down need to balance. So our up and down already balance. So we are going to have a rightward arrow, and we need to make sure that it's going to be larger than the left side, but we also have to double check to make sure there is going to be one to that side. So the rightward force is the applied force. So this one would be F applied. Now it says to consider friction. So if this guy is getting pushed to the right and is accelerating to the right, what force would be going against it? Well, it says consider them. Friction. God bless you. Friction always goes opposite to the direction of motion. Now, since it's accelerating to the right, okay, that means we will have a net force to the right. So when we draw in our friction force arrow, our vector, is it going to be the same size, bigger, or smaller than the applied force? Well, if it's the same, if it would be the same, then there wouldn't be a net force, right? Well, if it's bigger, then the net force would be going to the left, and it would be accelerating to the left. So it needs to be smaller. All right, so we would have a smaller arrow to the left, and that will be our friction force. And this would be our answer there. Just like that. All right, now they're saying, cool, same scenario. Rightward force is applied to this book to push it across the desk, but this time it says, is it accelerating? No, they're pushing it across at a, what does constant velocity mean again? That the what has to be? Net force has to be equal to 0. And what does that mean? Everything must So again, you have your horizontal surface. All right, we're on a desk. Here's our book. We already know Fg down and normal force up because they're on a flat surface and it's not accelerating upward, downward. So those two are going to be equal. We have an applied force to the right. It still says consider friction force and ignore air resistance. So our applied force has got to be to the right because our rightward force is applied force to the right. In order to move it across the desk, all right, to the rightward at a constant velocity. So our applied force is to the right. Now, how would I draw in the friction arrow? Same size, bigger, or smaller? Well, if it's smaller, then it would be just like this one, and it would have a net force and accelerate to the right. We just said constant velocity means the net force is 0. So if the net force is 0, everything must balance, which means all the top and bottom arrow need to be the same size and balance, and so do the left and right. So what size are we making the friction arrow then? Same size. Good. All right, as close as you can. Doesn't have to be fully perfect. And label that as your friction force. And that would be the answer to this one. Skydiver in number 8. Skydivers descending with a constant velocity. Consider air resistance. Okay, so here's our skydiver. What are we always going to have here? Weight, in which we go down. And what do we label that as? Fg. Well, is there a key phrase in here? Yes, there is. Constant velocity. So what does that mean? F net is 0. Everything must balance. So what does that mean? We have to have a vector going what direction to balance? Do you know? Up. Same size? Yes, because we need the net force to be 0. Okay, so we just need to figure out what this is. Well, it tells us to consider air resistance. Because we're not on a surface, it's not going to be Fn. This one, it's going to be our air resistance. And we want to show that those two are equal. Number 9, a force is applied to the right to drag a sled across some snow with a rightward acceleration. So this is going to be just like number 6. All right, we are on a flat surface. Acceleration is to the right, which means our net force needs to be to the right. Since we're on a flat surface, we have Fg and we have Fn. They're going to be equal. Again, rightward acceleration, so we have an applied force to the right. How many people have walked through the snow before? Is there friction? Yeah. So we are going to have some friction, but it's got to be smaller than the applied force in order to still accelerate in that direction. So we'll make a quick smaller arrow here as our friction force. And then finally, the last one. So when a car is coasting to the right and slowing down, it wants you to draw a free body diagram for that. So for this, when we say coasting, that means basically we're taking our foot off the gas, aka no applied force. So we're coasting to the right and it's slowing down. Well, what slows something down, guys? Friction, right? Goes opposite the direction of motion. So what we would do is we would draw in our box on the road on a flat surface. So we have weight down, normal force up, which will be equal to each other. So imagine, right, we're driving our car down the road to the right, and we take our foot off the gas. So there goes the applied force, which would have been this. All right, we have our applied force. So you turn onto your block. All right, you have the applied force going. And then you build up a certain amount of speed and you take your foot off the gas. What's going to happen to your car? Friction goes opposite to the motion, which is why we have it pointing to the left. But the car is still moving to the right until it slows all the way down. And then the friction force would disappear and we would just be kind of looking at something that would look like this.